Hello, and welcome to Dynamics is Fun. Now, we're going to go to our lines to see what questions people are having with this problem. Thank you. Hello, caller 1. What is your question?
Well, yes. Can we assume that there's a normal force from the belt acting on disc B?
Unfortunately, you cannot assume that, caller 1. Thank you for calling in. Let's go to another caller to see what other questions there are. Hello, caller 2. What is your question?
Okay, so what I was wondering is, there has to be an angular velocity in those discs. So what I'm thinking, the angular velocity of disc A is the same as disc B, right?
Unfortunately, that is not correct, caller number 2. Thank you. Check back on Friday to see our winners and their huge engineering packet. Thanks. See you then. Welcome back. Here we have one of our winners of our Challenge of the Week. Would you like to introduce yourself?
Yeah, I'm Gus. I'm really excited to be on the show. And it was challenging, but we got it. So
Cool. Welcome, Emmanuel. This is the second partner who helped solve this problem. How are you feeling? Are you excited to be here?
Oh, I am feeling great. I just love being in the show, okay? And solving this problem. I mean, it was a really difficult time, and a lot of time was spent into this that I almost yanked my hair out. But it worked out in the end, and I'm really glad to be here to solve it for you.
All right, sounds great.
So, starting off with the problem, we know that there are two discs, and we knew that disc A is spinning counterclockwise. And as it's doing that, it's pulling a cord, creating tension 1, and which is rising disc B up, which is and at disc B we're having a clockwise rotation. So as we're taking the sum of the moments, we're creating a for disc A. When we take sum of the moments about the center, we're going to make a we're going to call counterclockwise positive, and for disc B, when we take sum of the moments, we're going to consider clockwise to be positive. So they're going in two different directions. One note, when we're calculating omega, omega is not the same as this B. For omega at A, it's just V equals omega R. But for omega at B, it's V equals omega 2R. And that is because we discovered that the this B, there is an IC point occurring in the end. Now I'm going to leave the rest of it to my buddy Gus.
thank you. So, looking at disc B, decided to use angular impulse and momentum to solve for T1. So inputting our values, we get T1 is equal to negative 1.629 over T2, little t2 plus 7. And then from there, we took this equation, the angular impulse and momentum for disc A, input our values to get this, and then from there, solve for T1. So now using these two equations, we set them equal to each other, and from there solve for time 2, and got 0.56 seconds. And that's your answer for the first part of the question. From there, it's pretty simple. Plug it back into your T1s. Either one would be fine. We decided to use this one right here. And we got T1, the tension in this the belt at this point, to be 4.05 pounds. Thank you.